Hi, this is ET370 Lecture 5. This is going to be a three-part lecture. In this first part, we're going to go over the simple NPN and PNP tester circuit, look at some equations that are relevant only for the forward active state, and then look at this Darlington pair. It's a kind of a unique configuration to get extra high gain. In the next two parts, we'll look at this thing called large signal DC analysis. It's a nice tool, and we'll do an NPN lecture and a PNP lecture. But let's begin on this NPN and PNP test circuit. Okay, so I created this test circuit. It's actually to test an actual tip 102 and a tip 107 NPN and PNP transistor. And so if you look here, this is actually a tip 102 and a tip 107. This is the NPN type. This is the PNP type. And this is what the chip looks like here. Okay, and so you have 1, 2, 3, and I believe it's 1 is base. It's hard to see here. Let me see if I can get this zoomed in here. So it's hard to see, but there it is. 1 is base, 2 is collector, and 3 is emitter for both the NPN and the PNP. So base, collector, emitter, base, collector, emitter. It's kind of alphabetical order there. Okay, so I physically built this, but the chip would go here, okay? And remember, this is your base. Let me even put it in here. This is your base. This is your collector. Remember, the emitter is always attached to the arrow. Same with over here, base, and then the emitter is attached to the arrow and the collector. Okay, so how does this work? Well, I have a little LED here and a button, and I have this is like a battery or a voltage supply. And the way I built this is so that I can test does this work or not? Because some of these came out burned. So if I push this button, let's see what happens. I push this button, the energy from the battery is able to go through the button, through the base current limiting resistor, and then through to the emitter and complete the circuit. And remember, these NPNs are current controlled. Well, both of them, BJTs are current controlled. And the current going through here is going to allow current to go through the C to E junction here, which means the LED will light on. Okay, when they release it, no current flows are here, which means no current flows are here. The LED turns off. Very simple. And then the PNP side, we go over here and we go, okay, it's similar, but this time when I push the button, current is allowed to come from the high voltage source and leave the base. Here it's entering the base, here it's leaving the base. And if current goes and leaves the base, then current's also going to come through, a larger current's going to go through the EC terminals and then light up the LED when I release the button. No current's allowed here, therefore no current's allowed here. And this would be a very similar setup to how you would use it if you had a real load, like a motor or something. If I'm able to sink current out of the PNP, a motor would spin, right, in this configuration. In this case, if I'm able to source current into the base, this motor would spin, okay? So these are two very practical implementations of an NPN and a PNP. And notice the orientation. Notice how the NPN is kind of on the bottom of the load, more on the ground side. And here the PNP is on the high side, where the ground side is down here. That makes sense. So I actually physically made these circuits here. And so let me just show you the implementation. So here's the PNP and here's the NPN. Oh, where's the NPN? Oh, I think the NPN is over here. NPN is right here. Okay. And so this is my PNP circuit, and here's my NPN circuit. And I know these two are small, but this is, I actually printed out the circuit diagram. And you can see I have the chip here, the button here. This is my little button. I have my LED, and let's see if this matches what we saw before. I have a battery that connects into these two terminals, high and low voltage. When I press the button, what happens? The current from the high positive side goes through the base limiting resistor into the base. Great. And then what happens now is that this voltage can go through the LED, the resistor, into the collector and out the emitter and back to the source. Okay, so that's this guy. I go over here, this is the PNP side. It's very similar, except remember the transistor is now on the high side. When I press the button, what happens? When I press the button, I have the current that's able to go from the emitter through the base and back into ground. And that also allows current to go from the emitter through the collector, through the LED and the resistor into ground. Okay, so similar setup. And in fact, we can even run it. I have my voltage supply here. I have two leads, and I just got to make sure I have it labeled ground and power. So this is the ground, and this is the power here. Okay. and I can turn on my power supply. And right now it's off, power's on. And when I push the button, yay, it works. Now, if I take the same thing, and I don't have very much voltage here. This is like 6 volts right now. And so if I put, again, ground here, listen, let me double check ground. Yep, it's on the bottom one. And I put power to the top one here. So power 6 volts, okay? Very little voltage. And if I press the button, ooh, what's going on? Push that in a little bit tighter. Is that on? There we go, okay? Perfect. So that works. That PNP tester circuit, NPN tester circuit works. Okay, so this is just a very simple practical application of how these things work. And if you want to get a close-up view, here we go. You can see the implementation. Hopefully that focuses. Let me see here if I can do this. Focus. There we go. Perfect. And then you can see if I rotate, you can see all the traces that are cut on the back. Okay. All right, so I hope that was kind of cool. All right, so let's move on, and let me turn off my little power supply here. Okay, so I'm going to put this over here as a side. And if you recall, we had four states of this NPN, PNP. And what are the four? Well, yeah, what are the 4 states? There's cutoff, there's saturation, there's forward active, and then there's reverse active, which we just ignore. So really only 3 states. And for you guys, you kind of only care about like on and off, right? Cutoff, saturation, or the high level, like the bleeding edge of forward active. Okay, so in forward active, and remember, forward active is kind of like the throttle position, right? Where you can actually vary. Well, what happens during that state? So in forward active, you have some equations that are valid. They're not valid for cutoff, not valid for saturation. These are the 2 equations. One is IC and IE, which, what is IC and IE again? IC and IE are the current here and the current here. IC and IE are close in value. So if you look at their ratio, you can define it by alpha. IC over IE is alpha. So this is going to be approximately 1, 0.9, 0.99, nearly unity. This is alpha, right, or symbol for alpha. Okay, now what about the base current to the collector current? Well, that's going to be much bigger. You want a small current in for a large current here. So IC is proportional, but much larger than IB. And now you're going to use this new variable called beta. And so beta will be like 25, 100, 1,000. So this is our gain of the transistor. And in fact, they're actually both of these. If you know one, you actually get to know the other, right? If you know alpha, beta, you can find alpha. If you know alpha, you actually know beta, right? And another word for beta on a data sheet is actually HFE. So if you look on the data sheets, in fact, we have our data sheet right here. You can see our data sheet right there. There's actually an HFE, and again, I'll pull it up. HFE, and you can see there's a wide variance, 1,000 to 20,000 here, right, for this particular transistor. All right, so HFE for this guy. Okay, all right. So why is this true, right? So we got these 2 gains here, right? This one's close to unity. This is saying that the base current and the collector current is there's a large ratio here. But maybe let's look really quickly. Why are these true? Where did those come from? Well, if we go back to, this is a very simple proof. If we go back to our NPN transistor, remember IC goes down, IE leaves, IB goes into the base, easy. And remember, we can actually use a KCL to put all these currents together. So IB plus IC equals IE, easy. Now we can put in our new definitions. What is IE? IE is IC over alpha. Perfect. What is IB? IB is IC over beta. I just swap those, easy. And so I'm going to just plug them in. Look at this. Watch. I put IB for this one, IC over beta. And I'm going to IE here, IC over alpha. Great. So now I have one equation with just IC. And look, the ICs are all going to cancel. So I have 1 plus 1 over beta equals 1 over alpha. And I can solve it either way. I can solve it either for alpha or beta, and I'm going to get these 2 equations, right? So if I go this way, look at this. I can do a trick. I can say, hey, that's beta over beta. Boom. I can combine the denominators. Boom. Beta plus 1 over beta, and just solve for alpha by inverting. That's easy. Okay, so that's that one. Okay, what about this one? I can do the same trick. I can bring the 1 over to the other side, minus 1. Alpha over alpha, easy. Combine the alphas, denominator, great. And then invert, alpha over 1 minus alpha, boom. So a super easy proof to show that these 2 equations are true. But the main concept is this beta. That beta, also called HFE, that's a large number. Okay, so here's a very almost, stupid simple example. NPN transistor, if you have beta is 100 and you have IB is 1 milliamp, okay, what is IC and what is IE? Super simple. Well, IC is just 100 times that, and we of course have to assume it's in forward active. So instead of 1 milliamp, IC here is 100 milliamps. Super easy. Well, what about IE? Well, IE, we can find that from alpha. Alpha, we use this equation here. Solve for alpha. Look at this. It's 100 over 101, which is nearly close to 1. So IE is just IC over alpha, which is now 101 milliamps. And so this is good. Small IB, big IC and IE, and IC and IE are very close in value. Okay. If I plug these back into the KCL, into that KCL, they'd all agree. Make that equation happy. Okay, the last thing I want to go over in this short lecture is a Darlington pair. So the question is there a way to get a larger beta, aka HFE, right, in that forward active state, right? So is there a way to actually combine transistors and get a larger one? And yes, there is. You can actually combine two transistors that have beta 1 and beta 2. And if you combine it in this Darlington pair way, the new beta equivalent will actually be beta 1 plus beta 2 plus the multiplication of beta 1 plus beta 2. What does that mean? Well, that means if I have beta 1 as 100 and beta 2 is 150, you're going to get a beta equivalent on the order of 15,250, right? It's very large relative to the other ones, right? So you take two small betas and you get a super large beta. That's kind of cool. All right, so what does the Darlington pair circuit look like? It looks like this. You take these two transistors and kind of butt them up so that the emitter of one feeds into the base of the other, and you make the collectors connected. You have kind of this super transistor, which we call a Darlington pair. All right. And this is kind of neat. It's actually a very practical circuit and used in industry. In fact, this tip 102 and tip 107 is a Darlington pair, right? Look at that. You got the two transistors just side by side so that you get your really big HFE value, okay? All right, so how does that come out to be, right? Where is this super large beta coming from? Well, if I look at this and I look at this, we have this beta equivalent is IC over IB, where this is also IC over IB, right? So if I want these two to behave the same, this IC is the same as that IC. By KCL, this IC is the same as IC1 plus IC2. And this IB is the same as IB1. I wrote that here. So I can substitute that in, great. Now if I go here, I can break it apart. I have the same denominator here, IC1 over IB1, IC2 over IB1. Well, what's IC2? IC2 is this guy, and IC2 is the same as IB2 beta 2 right here. Okay, that's our forward active equation. Also, IC1 over IB1 is also beta 1. So what do we have? We have beta 1, okay? We have beta 2 from this one, and we have IB2 over IB1. Great. Okay, look, we're almost there. Beta 1 there, we have a beta 2 there. We're almost there. So IB2 over IB1, what is that? IB2 and IB1, well, what do we have? IB2 is equal to IB1, right, plus IC1. Can you see that? IB2 is equal to IB1 plus IC1 because IB2 is the same as IE1, right? So treating this as a node. So I'm going to substitute this in there. And what do I get? IB1 plus IC1 and then the same denominator. And look at this, IB1 over IB1, that's easy, that's 1. IC1 over IB1, that's the same as this one, beta 1. And so I get something clean. I get beta 1 plus beta 2 times 1 plus beta 1. We're done. Beta 1 plus beta 2 plus beta 1, beta 2. That's this guy. Okay, simple proof just by inspection of this to show that we get this nice super gain, right? Okay, so that's the Darlington pair that's actually implemented in industry in a standard component. Okay, well, I hope this lecture was useful, and I look forward to seeing you in the next one.